Good evening, friends, and welcome to today's webinar. We will be discussing about lasso regression. Um, before lasso regression, we need to understand the linear regression in itself. So, when I talk about regression analysis, we try to predict an output variable. So here I have y, which is output variable, which is also called as dependent variable. And this, of course, is an independent variable. We everybody knows this. I'm assuming everybody is aware of these concepts. So this is input and that is output. And using input, we are trying to predict output. So here we'll get an equation. That equation is equals to y is equals to beta naught plus beta 1 x. Right? So let us talk about how exactly these equations are calculated. This equation has coefficients which play the key role in predicting the y output variable. So first we look into the linear relationship. Scatter diagram is looking into various things. Now, okay, let me ask you this question. What are the various things that scatter diagram help us understand? Yeah, guys, please be vocal, please participate.
Linearity,
Right? Correlation,
correlation,
strength. Very good, very good.
and what was that?
So scatter plot to begin with is a bivariate visualization, bivariate data visualization. And it is talking about relationship between two quantitative variables. Alright? Now when we look into the scatter diagram, these are a few examples. I have only two variables, remember that. X-axis and Y-axis. And when we try to interpret these graphs, these plots, we will be able to identify whether the relationship is linear or not, straight line. So what is the relationship? This can be interpreted. Next, we can also see what is the influence of x on y, whether it is directly proportionate or whether it is inversely proportionate. So that is given by direction, whether it is positive direction or negative direction. Positive direction means as x increases, y also increase. So the line goes upwards. Whereas negative direction means as x increases, y decrease. So the line comes down. Now the third thing we can talk about is the strength of the relationship. And here we can talk about three levels of strength. One is weak, moderate, and finally we also have strong relationship. But we already know that the scatter diagram is subjective in nature because by looking at this visualization, different people might have different opinions. So we have a measure for this correlation, and that is called as correlation coefficient, which is represented using small r. And we know that the range is from -1 to +1. 0 means there is no linear relationship, right? So this interpretation is already known for us. So using scatter diagram and correlation coefficient, we try to evaluate the relationship between two, two variables. And when we find the relationship when being strong and all that, we come up with this equation, linear regression, equation of a straight line. And what is that logic which is being applied for prediction here? Yeah. What is the concept that linear regression takes for prediction? Dependency of an error variable on another. Okay. one variable or another. The predicted points need to be close as possible to the line. Very good. That's right, Madhusudan. What is the concept? What is the logic called as? That logic called as? How do we calculate that line which gives us, yeah, predicted values as close as possible to the, exactly, yeah, that's right, guys. So OLS, ordinary least squares. Okay, what does SH means? Okay, so, okay, short name, fine. Please use complete names, guys. It's really difficult to read out your names if you use abbreviations here. All right, so that's right, Shilpi. We are using ordinary least squares. So here, if I have to talk about this in mathematical terms, in vector forms representation, we are trying to find out this output using constants x1, and we'll have error term, right? And if I have to explain this in this form, the ordinary least squares is trying to find out a line which fits this data perfectly. I mean, which tries to fit the data the best it can, as good as it can. Right? So that means we are trying to reduce this error. So this is your equation of the line, which is given by beta naught plus beta 1 x. Right? And we are saying that we will be predicting the line, the data point. Let's say a new data point is xi. Assume that xi is here. We don't know what is the value, corresponding value of y for this x. So what we say, we try to plot this from here to that x1, xi, and wherever this line meets, wherever this xi meets the line, that would be your y of I, right? So using this equation, we are predicting y of I. Good enough. So the logic of ordinary least squares is assuming that the data points fall on that straight line, and we try to come up with a line which tries to fit this data appropriately. So what we do, we check this distance, all these distances are measured, and then we take squared distances, because if I take the sum of all these distances, it would become evened out, and the result would be 0. I will not be able to evaluate or measure the appropriate distances. Hence, we take squared distances. That's what your least squares means. And we are trying to reduce the sum of the errors. Right? So if I have to mention this data point, that is nothing but your y, which is equal to this data point, which is given by beta naught plus beta 1 x, and this error term, this is epsilon. Right? So this is what your equation is all about, equation of straight line. And when I say this equation is giving you the actual value, which is this one, what is the error, or epsilon or e or whatever that you want to write, that is y minus beta naught plus beta 1 x, xi. You can say x, yi or xi, whatever that you want. So this is your error term, and we're writing this as predicted value or estimated value as y hat. Right. So if you remember, we did this ordinary least squares on adipose tissue and waist circumference example. Generally, that is the example that we use. And what we try to do, we try to fit the line such that it passes through maximum data points, right? Now let me go to this. There is a website which talks about this. So this is a data set that I have. Let me explain this. So this is a data set, randomly generated data set. And for this data set, we are generating that line, right? So when I have the equation y is equals to beta naught plus beta 1 x, I get a straight line, right? And remember, we try to do a lot of transformations and all that to get the best accuracy. Let me do that and show you. So let me attach this and directly build a regression line. And if I say summary, the R squared value is 0.67, right? And we were trying to fit this. Let me show you the visualization as well. I need predicted values here. And this is the ggplot that I have. So if you see, this is a straight line that we are drawing. But the accuracy of this is really less, right? It's really low. So this is what I was talking about, calculation of error. We can calculate the error in multiple ways. But yeah, if I take this, it is going to be eventually become 0. If I take this, it is not giving me the absolute values. It gives us a value which is modulus, and we are not able to nullify the predictions here. Well, some issues are anyways, we are not going into in details of this calculation. And this is the most famous calculation, OLS, ordinary least squares, where we take square distances. And we try to minimize this distance, right? And the accuracy of this overall model is given by this R squared value. Yeah, R squared value is called as coefficient of determination, which can lie from 0 to 1. In other words, this is talking about the effect of x on y, which is nothing but beta 1 times. Beta 1 is the effect of x on y, right? Now, for calculation, if I take R squared value, this is the formula. It can be derived statistically. Just look into the actual values and predicted values. You take square of that. Yeah, you take mean. All these calculations, you have R squared value. The problem with R squared value is that whenever I add new variables, it tends to either increase or remain constant. R squared will not come down. Okay, it will never decrease. So how can I evaluate a model by adding few variables? It would be a challenge, right? Hence we have something called as adjusted R squared. Adjusted R squared is basically looking into the dependency or correlation. Yeah, it increases only when new variable adds to the prediction model's accuracy. So degrees of freedom is considered so that it is not affecting the number of variables. It is not affected by number of variables, input variables. Okay, so this is about measuring the accuracy. Now, there are few assumptions that we look into. Regression insights, linearity should be there and all that. One of the ways to remember R squared value is about the correlation between observed values and predicted values. So if I calculate y hat, if I predict y hat, this is my predicted value. I also know what is my actual value. If I try to see what is the correlation value, I'll get R value. If I square this, it is nothing but r squared y. Okay, this is one of the ways to remember. Stronger the r squared, that means more and more data points converge here. This is a plot between predicted values and actual values. Okay, so there should be symmetrical across this line in this form. If I draw a line, it has to the data point should be symmetrical. Stronger the relationship, more stronger the r squared. Okay, so this is one of the ways to interpret it. Now you know other homoscedasticity and all those issues. Now there is one concept called as bias and variance. See, we are trying to ultimately increase what? Accuracy of the model, right? So this is my initial equation. It is written as theta values, but it is beta naught plus beta 1 x. So it's a straight line. But if I have to try and predict the values properly on my training data, see basically what we do, historical data will be split into training data plus validation data. Okay, I'll come back to that. So when I am predicting the models, I will predict the models. I will predict the models on training data. I'll build the models, right? Using this training data. When I build this model, I'll try to measure the accuracy, the performance of the model. And if it is not accurate, then I'm going to tweak the parameters, input parameters, transform the data and all that. And then I'll again rebuild another model. So I'll be building multiple models and verifying the accuracy. So here, basically I'll have model 1, model 2, model 3, all these kind of models. And these candidate models will have varied accuracies. So I'm going to basically try to fit a line, a regression line, onto this training data, right? So we are trying to minimize the error. So that's what you are trying to do in this equation as well, in this lines as well. This is a straight line which is not passing through all the data points. So the error that you get would be higher. If I try to do this, yeah, it might just work out for the data. But if I try to do this, yeah, I'm trying to fit the line perfectly for this training data. So it might not work on test data or validation data. Okay, think a question. While building a model, do we need to build on whole data set or on training data set and apply this data set? We partition, always we try to build the models on training data and validate that on validation data. Partition needs to be done. Okay, so when I try to build these models and try to reduce the error so that the data fits, sorry, the line fits the data, you will get least error, right? So this is called as overfit. Let me show you that. So this is my straight line equation where I'm taking degrees of my degrees of polynomial model as 1, sorry, not 0, it is 1. So when we begin at this equation, but when my data is like this, which is not in a straight line, I might have to work out with polynomial models. And when I say polynomial models, I will have to increase the input parameters. I am trying to bring in more and more variables into the equation. So the complexity of the model also increases here. If you see, this is a straight line and the degree is 1. When I increase the degree, what happened to the line? The line became curved, right? It's no more a straight line. So it is trying to fit data points. If I increase furthermore, it becomes again a little more curvy. Degrees of 4, 5 degrees. So if you see, it is trying to touch all the data points. 6. 7 is where it touches all the data points. It is capturing everything here. Right? So this is overfitting the data. Now this is your training data, right? When you verify this equation on validation data, your validation data might be somewhere here. So this equation will throw a lot of error when you're working with validation data. This is termed as overfitting. So this is called as overfitting. So first we try to build an equation and we try to reduce the error. When we try to reduce the error, we try to increase the complexity of the model, that is increase the number of input parameters and all that, so that my R squared increases, right? But what is the right value of R squared? Till what extent should I increase? If I keep on doing that, I might end up with an equation like this, which is having an overfit condition, right? So overfit means you have high variance, underfit means you have bias. So understand bias and variance, right? So in simple terms, bias means we have less features, okay? And if you're trying to predict a value y, you might end up getting error, a lot of error. You'll not be able to predict it properly because you don't have values, less features are there. So you're biasing your model using only few features. But when I say variance, then we will have too many variables, so too much of variance is captured. That means we have high number of features, and this will have less error for only training data. This is high error both on training data and validation data, but here less error for training data, whereas very high error on validation data, because we are trying to fit, somehow forcefully fit the equation only on this data. So error might be 0 also. You're perfectly predicting the values, but the same thing might not work on this. So your error will be very high. Okay, this is the concept of variance and bias. Now if I have more bias, if the model is underfitting, we know what we do. We do transformations, we bring in new features, try and increase the accuracy. So one way is to increase features. It will of course increase the complexity as well. When we have high variance, that is if you are overfitting, then we have to decrease the number of features that we are using in the model. So you are trying to decrease the complexity. So this is not an issue. This is what we get, and we try to increase the accuracy by increasing features and all that. But when we have high variance, when the data is when the model is overfitting the data, we need to do some feature selection. Okay, we have to somehow minimize this values, and in order to do that, you have two options. One is reduce the model complexity by selecting few features. Yeah, so you might do it manually by doing a feature selection and passing only those features for your ordinary least squares. This is one way. Okay, I see a lot of questions coming in. Let me just look into these questions, try to answer them. Adding more variables to the equation means it is no more linear model, right? Of course, it might not be linear model. You're talking about polynomial model here. The once transformation is done, do we need to do back transformation, means bringing back the original unit? Why you want to do that, Anu? Yeah, think on that back transformation. Why you want to do that? Minimize means do we need to remove few variables? Yes, obviously you are trying to do feature selection, Chandrakanta. So we'll remove a lot of unwanted variables, right? And one of the other methods, I mean, this is a tedious task if you have high dimensional data. Now, if you have 1, 2, 3, maximum 10 variables also, your regression equation is very easy. But what if you have 100 variables or 200 variables? Yeah, it becomes a challenge, right? So in such cases where you have very high dimensions, then regularization will work out. Now, what exactly is regularization? This is also called as normalization. Okay, let me answer Anup's question. Square root of y is equals to beta naught plus beta 1 whole square. Okay, let me write Anup's square root of y is equals to beta naught plus beta 1 x whole square. Okay, so there's nothing but whole power 4, you can think of that way. If you're applying transformation on y, obviously you need your y back, right? So in that case, what will you do if you need y? Yeah, no? If you need your y value, what will you do? You apply square of your end result. Once you have predicted y hat, the result would be like this. You're going to square this value so that you'll get y hat. You'll be using this value. When you're applying transformations only for input, back transformation is not required. I was talking about only this input variable transformation. Okay, Suresh, we can do PCA to reduce dimension. Yes, absolutely, you can do that. That is one of the techniques that you can apply. When the model fails for validation data, then we have to back, if I am not wrong. Not sure what you are trying to answer there, what you are trying to say. Okay, hope I got the answer. Okay, nice. Now, what exactly is regularization? So, first is regression technique is try to come up with an equation which is trying to predict the value, right? And when we are trying to predict, we are trying to minimize the error term. And error term is nothing but actual value minus predicted value. So we try to minimize this. So how can we minimize this? By optimizing these coefficients. So this is your equation. Error. So this is nothing but your y hat. So we are trying to minimize this. And in order to minimize this, we tweak beta naught at beta 1. Right? So regularization is used to overcome this overfitting problem. Yeah, it's a solution that can be applied for overfitting problem. It's also called as normalization, or normalizing patterns, or regularizing parameters. So what this means is your equation, right? When you have this equation, let's say you have multiple input parameters, okay, we generally don't apply this lasso regression or regularization terms when you have a single parameter. We need at least two parameters, okay, minimum is two. These regularization concepts are applied when you have high dimensional data, so that you can also handle collinearity problem as well. Okay, regularization will also solve your collinearity problem without deleting the parameters. So here, normalizing parameters or regularizing parameters means we try to bring the values of all these coefficients similar. Because if I have this equation, and if I have larger value for, let's say, beta 2, what happens for the prediction if I change a small change, if I bring a small change into this? The y is getting affected heavily, right? Because of this high value on the coefficient. So it is normalizing these parameters. Now in regularization, one of the concept is lasso, which is used for feature selection as well. So if you have 200 features, we can do a feature selection. Out of these 200, you might select only 20 or 50 odd features. That can be done using lasso. It's also called as shrinkage technique. So you're shrinking your features. It works when you have high dimensional data, and it makes coefficients similar, smaller values. It will keep all the values constant, and that too small values. Because I just explained, if we have large values for coefficients, even with a small change, the overall result, that is y value, will get affected heavily. Yeah. Now feature selection means zero value can be put into beta values. If I put beta 1 as 0, what happens? X1 is not considered in your prediction model. This is nothing but feature selection property. Okay. So this is about regularization, why we use regularization. Now in regularization there are various methods. The most famous, predominantly used ones are L1 and L2 regularizations. So what is L1 regularization? It is called as lasso. Lasso means least absolute shrinkage and selection operator. So least absolute. So we are taking absolute value. And this is the equation. If you observe this equation, the first part, this part, is nothing but your error term. So this is called as error function. Yeah. Now for this error function, we are trying to add a penalty. This is called as a regularized term, regular term. It is also called as penalty. Okay. And here we are using mod value, modulus of coefficients. And this lambda is a constant which is getting affected, which is changed. Okay, with different values of lambda are taken. And this is L1 because here the p value, that, let's say if I have p here, the power p, it is 1. Hence it is called as L1 regularization. Right? So when I have lambda as 0, what happens? This L1 regularization becomes OLS technique. Right? It simply becomes OLS. Whereas if I take this as infinite, lambda as infinite, very large value, then what we assume? We assume that you can ignore this because this is infinite, this value becomes negligible. Okay, you can nullify that. Now when you have it as very huge value, we try to make this value smaller by taking this as 0. Right? So this is what happens. Lasso regression will either keep coefficients very small, or it might take coefficients as 0. This one. Right? So when it is doing this, it is trying to underfit. I mean, it has very high bias. It will not be able to overfit the data. So whenever you have overfitted data, we try to apply this so that it becomes a little bit of underfit. It controls the overfitting issues. And because it's a constant, lambda is a constant amount. We try to set this constant. It can be 0.1, 0.01, 0.5, 0.8, 1, 2, 5, whatever that value is. It's a constant value that we are setting. And this is called as penalty, so that we can reduce this value. I mean, when we are trying to see, this is basically what this regularization is used when you are having overfitting. Overfitting means this becomes 0, right? So we are trying to make sure that it does not become 0. So we'll see it tends to make coefficient 0. Okay, there is a statistical calculation that is applied. Let me just explain that. Lambda value is to be set up front. Yeah, it's a kind of trial and error, the method that we do. So you can apply this and see for different value of lambdas what is the best result that you're getting. Okay, so when I have, let's say, 200 features, 200 input parameters, I will get 200 beta values, right? So L1 regression, this regularization, which is lasso regression, applies these. When I apply this, it makes a lot of coefficients as 0. When I have this coefficients as 0, that means few of your parameter these input variables are ignored. So you'll have only few values that are considered in your regression equation. Yeah, hence it is also used for feature selection. Now, when I look into L2 regression, that is called as L2 regularization, it is called as ridge regression. Here we are taking squared values. So that means here the power is 2. Hence it is called as L2 regularization. So to the error term, we are trying to bring in squared coefficient values. There we are adding modulus of values. Here we are trying to add squared values. And here also, when this becomes 0, it simply becomes OLS. But if it becomes modulus, infinite, then the ridge regression, the difference that it has from lasso regression is that coefficients are not made. Coefficients are not made 0. Here, the coefficients are not becoming 0, but you will have a very small term, a small value. So the coefficients values are shrinked. The magnitude of coefficients is becoming very small. This is how underfitting is achieved. Remember, in ridge regression, coefficients are not ignored. We are not deleting any coefficients. That is, coefficients are not made as 0. Whereas in L1 regularization, we do that. So I want to take an empty sheet and I want to quickly explain one thing here, and then we can stop. All right. So see, basically, your equation, right? Your equation is y is equals to beta naught plus beta 1 x plus error. When I have multiple entries, yeah, I'm just taking a two-dimensional space, guys, just for explanation purpose. But as I told, lasso will be applied, or rich will be applied, or regularization will be applied when you have huge number of dimensions. So when I have multiple values here, let's say y of n is equals to beta naught plus beta 1 xn plus error n. So let me put this as 1. So 1. So this can be written as vectors y1, y2, y3, so on and so forth, yn. And these are summation of coefficients. Now this coefficient is beta naught and beta 1 are constant. Hence I'm simply saying n into beta naught plus beta 1 into 1, 1, 1, 1, 1. And here I'll have x1, x2, x3, so on and so forth, xn. And plus here I have error terms e1, e2, so on and so forth, en. Okay, this is how it is represented in vectors. Now your coefficient vector, which is written like this, is nothing but beta naught and beta 1 if I take only two dimensions, right? I have only beta naught and beta 1. Now L1 normalization is, it is written like this, vector form. We are taking mod of these values. That means modulus of beta naught plus modulus of beta 1. Okay, this is your L1 norm equation. Now if I take L2 norm, sorry, I have to see a question. Both overfitting and no, only overfitting conditions. When I take L2 norm, it is again written like this only. But here we take square. It's this is L1, so I'm writing L1. Here it is L2. Here I take square. That means we are doing a calculation like this: beta naught square plus beta 1 square. This is what I get, right? Now to explain this, let me draw these values, x and y plane. Okay, assume that your vector value, this is vector, so it is basically like this. Assume it is 2. Okay, so I have beta naught, here I have beta 1. So this is a vector which can be represented like this. And if your vector is equals to 2, when will I get this 2? Either it has to be 1 comma 1, right, or 0 and 1. So if I represent that here, beta naught would be 0, then beta 1 would be 0, then beta 1 is beta naught is 1. If I write it here, this is beta 1 is 0, beta naught is 0, but beta 1 is 1. Here also we are taking modulus, right? So it makes sense. We are only looking into the magnitude, not the negative values. So this is how you get the values. So your values that you get might end up on the corners of the square. These are the values that you will get, beta naught and beta 1 values. And the optimal value is, of course, beta both 1. So it tries to find out what is the best value of beta in a multi-dimensional space. This is for L1. But how can I draw an L2? So draw this. This is beta naught. This is beta 1, and this is a vector with 2. Now when I get this equation, right, I cannot put what do you say, zeros. So what I'll do is, this is a continuous value I'll get, right? So the L2 values will be like this. It can be any value here on this circle, the radius. You can take this value, you'll get some value, beta naught and beta 1. Here also you'll get some value, here also you'll get one value. So it does not limit itself for taking zeros. Okay? So this is about the vector calculation of L2 and L1 normalization. So in short, if I have to explain about lasso regression, or for example, ridge, okay, these are regularization techniques which are used when we have overfitting data. So these are used to make sure the data is not overfitting. Lasso is also called as shrinkage method. This is also called as feature selection method, etc., etc. But predominantly we use ridge. Of course, there is no reason why we should not use lasso regression. But lasso, right, it causes a lot of data loss. You can say that it will create a lot of data loss because it makes a lot of values as zero, a lot of coefficients as zero. Hence, a lot of data loss will be there. And ridge takes squared values, so it is calculation wise also, analytical wise also, explanation wise also, it makes more sense for us using ridge regression. So practically we can use both of them. This is predominantly used for feature selection. Okay. So let me quickly show you our code. Okay, this is for your linear regression. Let me clean this off. Okay, so let me load a data set here. So multiple ways of doing lasso and ridge regression, guys. It's not confined to this way. But here, this is the data set that we have. Okay, a lot of factor data is there. Hence, I am going to convert this data into factors. If you observe structure, you see these are all factors, right? Few of them are factors, so I'm converting them as factors. So I'm quickly running through the code because of the lack of time here. Now this model.matrix is converting this data frame into a matrix and also taking the factor values. So each level of the factor is taken as one row, one column in the matrix. So if you see house data, it's a large matrix, it's not a data frame. So this is how you'll have. So view 1, view 2, grade. These are all the factors for grades. And you have zip codes. So if you look at this, how many columns I have now? Right? Very, very high number of columns. So out of these, I'm first removing this intercept value. It is all ones here. So all are ones. So I'm removing that. And then I'm trying to convert these, normalize these individual columns. Okay. So I'm applying scale function here. I'll not be directly applying the scale function. I'll be using this for loop. Because if I use scale function and try to do the calculation, it takes a lot of time. Okay, so this is a simpler way to calculate that scale function, where we are taking mean and standard deviation of each column and subtracting that with the actual value, and you'll get that value. Okay, so we have done this, and if you see, this is the normalized data, which is called as X. Okay, now I'm installing last function. It's also called as least absolute regression. Different names are there. least absolute regression is what is unofficially called. This is a package. If you see question mark of that, it says least angle regression, which uses lasso and other regression types, forward stage wise, right? So you can go through that. It has variance of lasso regressions. What basically it is doing is it's splitting the data into 10 different samples. So that it has taken sample 1, it builds one model. So you'll get beta naught, beta 1. It takes sample 2, M2. Again you'll get a different beta 1, beta naught and beta 1. S3, S4, so on and so forth. You'll get 10 different samples. So 9 are being used for testing purpose, training purpose. So basically what we do is we take average of all these coefficients, beta naught and beta 1s. Beta naught average, beta 1 average. That's what Lasso is doing, and using that average, we test it on test data. So cd.lars is doing that. You can check what is that function. It takes a little while to actually execute because I'm trying to split the data into 10 different partitions and trying to calculate it. If you do question mark of Lars, it says compute k-fold cross-validated errors curves for Lars. So what is that you are getting when you are trying to do multiple regressions, multiple times the same regressions? What is the error value that you're getting? So this is the Lars function that I'm using. Here I'm saying trace is equals to true. I'm saving that value into lasso. So if you see, these are the values. And if you observe here, variables are being dropped. Few variables are being dropped. So if I see coefficients of this lasso, see a lot of variables are made zeros. So these are all your coefficients, guys. That means the variables are also zero. You don't have to consider them. Only the coefficients which have, only the variables which have some coefficients can be taken. Rest of them can be ignored. Okay, so we are not doing in detail lasso regression R code. We can schedule that some other time. I'll try to bring in the elastic net regression in the next webinar. We'll also try to see a gradient boost and a gradient descent regression and all that as part of the next webinar, and in that we'll try to look into the R code in detail. Any questions as part of as far as the regularizations of L1 and L2 are concerned? Any questions? No questions?
Sarath, I have a question. On what basis it is this algorithm making some of the features as zero? There might be some basis, right? Say there might be some criteria.
So it is trying to find out the best optimal value. And what is that best optimal value? Derivative is 0. So we are applying partial derivatives for this terms. So that cost function, if you have seen, it is nothing but error term, right? Error is y minus y hat whole square, plus you are penalizing this values using summation of coefficients, mod coefficients. So we want the least value here. When will I get least value? I have shown that vector form, right? This is beta naught plus beta 1. So if I want a value, then it will be on these edges. This would be the best values. So one of the values, one of the coefficients will become 0. And this is only a two-dimensional space that I'm trying to show. If you have, let's say, multi-dimensional space, then you'll have this kind of values. And to minimize, to get the minimum value of these errors, we are trying to remove few of the questions. We are trying to find what is that best value, and it automatically
Okay,
tells that the coefficients are 0.
okay, algorithm will itself take care whichever is having a highest error value, that will be make that coefficients as 0.
Yes, it tries to find out optimal minimum value here based on the
Okay,
lambda values that we are trying to pass. So it's a constant that we are trying to say that, yeah, the minimum value should be this much, not less than that.
okay. So do you have any constraint on k value, like at max, what the max k value can be given? Depends upon the features.
But you're
Or
talking
is it?
about lambda, is it?
Yeah,
Yeah, it's
lambda
a
value.
constant. It can be any value. It depends on what
Any
value.
value.
Yeah, it's a constant value.
Okay.
Madhusudan, I'll try to cover out that question in the next session. We are already crossed the limit, the time span. So unfortunately, I'll not be able to explain that in this session. All right. If no questions, then thank you so much, guys. Let's reconnect again in the next webinar. Have a wonderful time and keep practicing these things. Thank you, guys. Take care.